All right, welcome to the third part of the quick tutorial about the analysis of the micro-CT dataset acquired by the Siemens Invion platform micro-CT system using, or images will be processed using the Slicer3D software. So just to kind of do the summary of what we did in the previous step. So we, in step 1, we converted the files to the format readable by Slicer. In step 2, we cropped the data set to the region of interest or volume of interest, which contains only the organ that we are interested in. And we ended up actually with a file, which is very important because this contains the cropped volume. We don't need any header right now because the NRRD format contains the text or the parameters and also the binary file to load in the dataset into the slicer. So the size is much smaller than original. Original dataset was 3.5 gigabytes, so we have about 7-time reduction in the dataset. All right, so let's open up Slicer and load in the cropped volume. So we do this by going to data here, or we can just load data with this button. We need to indicate choose file to add to indicate where we keep our cropped data set open. It was recognized as a volume, so it's great. Click OK. And then after several seconds or so, it will be shown the 3 planes, so the axial, sagittal, and coronal plane for the dataset. Again, we can just browse the dataset in different planes, but this is not the focus of this part. So let's go to visualize, actually to render the dataset. So volume rendering, we choose the volume, cropped volume, then the preset, it will be CT bone here, and we chose also the renderer engine as a GPU, which is much faster than the CPU, and we need to visualize. So click this eye, and we have actually our data set rendered in 3D. So let's center it with the mouse wheel, zoom it like this. And using the shift slider here, we can reduce to show only bones. Of course, we can change different other kind of visualization elements. We can go here to the menu where we can uncheck or toggle the 3D cube and 3D axis label like that, or we can also change the background to the black, which I personally prefer. So what we have here, so right now we have a 3D volume. So this is a mouse hind limb, and now because we have prepared the data set, so now we can perform different type of analysis. This is a particular case that we are studying the model, the burn model, which causes actually formation of so-called ectopic bone fragment in the muscle. So we can see that there is a separate kind of like a area or the volume which contains actually bone. So this is due to this kind of treatment or the burn model. And there is also a tiny bone over here which kind of grows, which is a part of this study. So these are, this is one very unique study which is focused on measuring the volume of this so-called ectopic bone. So therefore, what we'll need to do, so we need to segment out the ectopic bone from the whole bone and calculate what will be the volume of those of this ectopic bone fragments. So there are different type of analysis possible, but many of the analysis will involve segmentation of the specific region or the volume of interest from the whole image. So this will be kind of a universal procedure that it can be used for other applications. So what we'll do first, we'll change the volume rendering. So I'm going actually to switch off the volume just to speed up the analysis process. And I'm going to change our layout just again to 4 up, just to have those 3 planes a little bit bigger. And we also switch the module to segment editor. So we'll look at different kind of segmentation of the bone. So as you can see, the CT image has different grayscales, and the for example, the white color, which is associated with a higher count value, it represents bone. So if the images were acquired and converted by the imaging scanner or express the pixel value in Hounsfield units, so the bones will be around 1,000 Hounsfield units, over 1,000 Hounsfield units. The tissue will be within about 50 to 100 or 200 Hounsfield units, and the air, so something which is not doesn't attenuate the X-rays, it will be within the range of 0 or negative values. So the first step, it will be to create a new segment. So we are working on the master volume, which is the file name cropped. So this is our cropped. Let's click the new segment, and I would like to choose the color. It's not required, but it's good to have, for example, and define that this will be a bone. But we don't see the kind of this color on this image. Well, because we didn't define how the bone will be segmented. So there are different techniques. One of the easiest one involves thresholding. So we can click threshold, and right now you can see that there is like a pulsating change of color, which shows actually the bone, or at least the pixels, which are within the threshold range from about 100 to max. So this is called actually auto to maximum thresholding. There are different methods for thresholding, so several of those. Let's use the OTSU, which is kind of like a one of the most commonly used. The thresholding for the bone is actually auto to maximum, which means that automatically it chooses the lower limit and the higher limit is the maximum. I mentioned that the bone is within thousands or hundreds of Hounsfield units up to several thousands. So here it's more kind of we use the auto value, but of course we can also change that. So let me increase the zoom. So with the right click pressed, I'm just moving the mouse so I can increase a little bit the zoom here. I can pane with clicking the middle button and moving. So we can see that there is bone is nicely shown here, but there are some small bone fragments which are still not included. For example, over here, So let's actually reduce this threshold. So if we go too small, so we are trying also to show the tissue. So let's go a bit higher. So I think in general we can have the number of 1000, which is pretty good approximation for the Hounsfield units for the bone. But of course, you know, in your data set could be a different ranges. But if we are happy with what we see, so it means that we can browse through the data set, which means that we are only segmenting out bone. I would probably reduce it a bit. Maybe let's do 800 range. That actually includes some of those bone fragments. Those faint bone fragments may be better. So between 800 to maximum. Keep it in mind if you are analyzing several of the images taken by the same scanner using the same protocol, so you may want actually to keep the lower range at the same values just for reproducibility of your results, because that's actually, this part is, it's more kind of subjective to the operator. But if you are happy with the bone as it is, so we just click apply. And right now we created actually the bone fragment, which is defined and color coded by the color that we chose here. So we can show 3D right now. So if we click 3D, so it will be rendered the bone fragment over here. So this is our bone fragment, which contains also the ectopic bone, right? It's very difficult actually to, it's impossible to segment out the ectopic bone from the other, or the normal bone, just based on the thresholding, because this bone has the same pixel values or within the same range as the bone. It's like a regular bone. So what we can do, well, we can create another region of interest and then manually take out or select the ectopic bone. So how we do that? Well, there are different procedures, but I would like to duplicate first the bone that we created in step 1. And how we do this? Well, let's create a new segment. I would change the color actually to maybe something like red. Select. I will call it actually the ectopic bone. And I will use the logical operator to add those two segments. So I'm going to add the bone and the ectopic bone together. Apply. So now we created identical, like it's almost like a duplication, identical segment which is independent from the bone. So we can, for example, switch off the bone from the visualization, and we can switch off the ectopic bone. In this case, it will be our original bone. So right now, from the ectopic bone segment, we will use the scissors and remove everything outside of the selected volume of interest. So how we do that? Well, first we need to visualize the ectopic bone. So click out the bone and visualize just only ectopic bone shown in the red color. Because we'll be operating now on the 3D dataset, so let's change the layout to conventional widescreen where we have the 3D dataset bigger. We can zoom it with the right mouse and in the middle mouse, so we can just reposition, and with the left mouse kind of rotate. So we can just rotate it, we can see those distinct bones, so we can select out. And now, keeping the ectopic bone selected, we will use the scissors. And the operation will be to erase everything outside the region of interest or volume of interest that we'll create. So now, what we'll do, we will select this large volume of interest like this, and it will remove. So now what we did, so we removed everything outside the volume of interest. So right now we have actually the bone, and we can now visualize the bone. And we have also the ectopic bone, which is just separate. So now, because we have this ectopic bone segment out, so we can perform so-called segment statistics just to calculate what is the volume of this. However, before we'll do this, because very often for presentations or for visualization, it's nice to have actually the nice image where we see the regular bone and also the ectopic bone. However, the bone here, this original bone, contains also the ectopic bone. So let's do another logical operator to remove the ectopic bone from the original bone. So how we do this? Well, let's keep the bone selected, the logical operator, subtract, and we'll subtract from the bone, we'll subtract the ectopic bone, and click apply. So after several seconds or so, what we'll see that from the original bone, which we included the ectopic bone was taken out, so removed. So now we have two distinct data sets or segments. One is a bone without ectopic bone, and one or data segment which contains only ectopic bone. So we can just visualize only the ectopic bone or only the bone without ectopic bone. So that's nice because right now we can create a nice picture. And let's say for the picture, we choose this kind of icon, like a photo camera icon. Let's click it. And it will ask us the name. So screenshot is fine, or 3D or whatever. And we need to select what will be the image that we want to collect. So in our case, it will be a 3D. So you can just right now call it a screenshot 3D or any other name. And we can also put some description, but if not needed, so we just click OK. So now we have image. So we segmented out bone. So we have a bone and ectopic bone. We took a picture. And finally, the last step, which is needed, is to calculate what is the volume of the ectopic bone. So how we do this? Well, we go to search segmentation, segment statistics. So when we start typing segm, we have actually segmentation statistics. Let's select that. And from the segmentation, we will create a new table. So we are not changing anything, just click apply. So now what it will do, it will take those segments. So we have now information about the bone segment and ectopic bone. So it tells us about the volume of the bone without ectopic segment and the ectopic segment. It will also tell us about some other kind of volumes using different other methods. But the first or the needed information for this particular project is the ectopic bone volume, which is expressed in cubic millimeters. In this case, it's 2.27756. We don't need to record this right now because after we click Save, so now we will have a whole bunch of different data or files to save. But let's choose the directory where we want to save all of them, because we had actually the directory created in the desktop called raw data. So let's keep it there. And of course the file name cropped. So this is the image file. Didn't change. We didn't do anything with this file, so that's why it's not checked. So let's leave it as it is. We have the screenshot 3D and PNG file, but we can format, we can change to JPEG, TIFF, BMP, whatever we want. And then the table, which is a tab separated value table, or it could be text, or it could be comma separated value. So tab separated value will be perfectly read by, let's say, Excel or calculational worksheet. So let's, and it will contain actually information from the segments of a volume. So let's save it. And after several seconds, it's a relatively quick process. So all data set is already saved. So let's close the slicer. We don't need anymore. And let's look at the content of our original folder. So right now we have PNG format screenshot, so we can open up. So we can see this, what we created. Beautiful. And we have also the tab separated values. So again, we can open this data using Excel sheet. I have here actually the LibreOffice calc. So let's open it up. And let's open it, desktop, raw data, and let's go to find our table. Here you go. Oh, I'm sorry, this is wrong. It's wrong file. We're looking at the table, not the table schema. Here you go. And now, because it's separated by the tab, so it will import and each value will be inserted in different cell. So that's good. It's a tab separated. So click OK. And we have our information. So we have the volume of the ectopic bone. We have the volume of the bone without ectopic bone. But for this particular project, so this is the information that we collect. So that concludes actually the analysis of the CT images acquired with the Siemens Invion system, and the analysis was performed using the Slicer3D.